Section 13.4 is called direction of rotation. And it's an interesting thing with a three-phase induction motor, but we have three phases of electricity, and these are just three phases of a sine wave that we're bringing into this motor. And they're staggered at 120 degrees in terms of their cycles. But it's interesting to find out that with a three-phase motor, a machine is going to turn in one direction. And if you swap out the connection, like if you take phase A and you place it where B is, and you put B where A was, you can change the rotation of the motor. So it's an important thing to be able to recognize. Sometimes you'll get in a situation and the motor will be turning in the wrong direction. I mean, if you have a vacuum, that motor that's driving that vacuum needs to be turning in the right way, because if you don't, you'll turn that vacuum into a pump. Okay, or maybe a conveyor needs to go a certain way. So you need to know and predict what the direction of rotation is going to be. Now, there's equipment that is made that you can make that determination prior to connection. But anyway, not to get into the particulars of a specific application, but I just want to show you why that occurs. And what we'll do, let's go back here and look at this figure 13.7. Okay, so what we're looking at here, we're seeing this particular sequence where with this sequence, we see that phase A is peaking here, and then 120 degrees later, phase B peaks, and then 120 degrees later, phase C peaks, and then that would cycle through to where, that would happen again here. That would be phase A, and so forth and so on. Now, if I looked at that, I would say that the phase sequence is A, B, C across there. And what we see with that is, a particular flux pattern that occurs with that sequence, okay? And, if for instance, this is showing a clockwise rotation with that sequence based on this. Now, what I could do is I could connect B. I could interchange any of these phases, okay? And when I do that, what happens is the field is going to turn in the opposite direction. And when the field turns in an opposite direction, then the actual motor is going to turn in an opposite way. So what I want you to take away from that is that swapping any two of the phases in a three-phase motor will cause the machine to reverse direction. Okay, so we use that a lot. There's actually a device that we can engage that to change the direction of a motor. All right, so important characteristic of a three-phase motor. The next thing I want to bring up to you in this section is that when I look at this, these are what you call salient poles. I mean, they actually, look like that in the interior of the motor. And early machines, early AC motors were built this way. And you sort of created these electromagnets by taking a coil of wire and wrapping around that protrusion, that salient pole, run current through there, causes this magnetic flux to occur, right? And so, all of that's going on. And what was found later was that, if I look right here, for instance, if I look right in here, there's a large gap between those two poles. So if I could create a different design that eliminated that lapse of or lack of coverage in those areas, I could get a more efficient machine that way. So the way that is remedied is shown in the next slide. So modern machines, they don't have the salient poles. They're replaced by this smooth stator. And so if I looked, with the, representation of that, I'm looking at this and I'm thinking about that in terms of phase one through there. And what I can see here, that would be that same connection, for that, right? Here goes through here, back to here, to neutral. And that would be for phase A, all right? And so, there are these, that's just the way that that it's constructed. Okay, so there's two coils for phase A. He calls one AA and one AN because this one, is connected to neutral, and this one is, just the coil designated by A, and they're lodged in slots on the inner surface of the stator. Each coil covers 180 degrees of the circumference, whereas the coils in 13.6 were only covering 60 degrees across, right? So you've made this machine much more efficient because it can produce more flux per turn, and a current like IA1 flowing through terminal A to neutral A would deliver a flux pattern that looks like what it's showing us here, okay? It's showing us this flux pattern here as that is created, okay? Now, the coils of phase B and C, they're identical to phase A, and they can be seen in this figure 13.9 B. And again, let me see if I can find and try to highlight that. Here is, it's a little too thick for that. But anyway, here is A. Let me select a different color. And here is B. Here. Okay. And then finally, here is C. C is in here. Well, it's overlapping. I apologize for that. But what I wanted to show you is that, they're all each offset, the particular amount of degrees that we would expect for the 360 degrees. They're displaced 120 degrees each by, the way that they're laid out into the stator, in terms of the representation of A to B and so forth and so on. And, the connection is, it's all the same for each one. And I guess the other thing that we should see is all of those patterns with the three phases, that they remain the same, just like they were before. But what we do now is, we've got this coverage through the entire interior of this stator, right? There's none of those gaps there where you can, the flux density is lacking. So you get a machine that's much more efficient that way. You don't, you're not losing or have those areas where the flux is less at any point. The actual direction in the rotation and all that stays the same in terms of the phase sequence and all that sort of thing. But, the combination that we're seeing through this connection as it is, we see these overall overriding flux patterns that are the result of that. And, the combination of the three phases give us that flux pattern. And again, those all are able to rotate in a certain direction. Okay, so if I look at ABC sequence, I'm going clockwise. If I go to ACB sequence, then I would cause it to go in the opposite direction. Okay, and then the last thing here in this section, he says in practice, instead of using a single coil per pole, as shown in 13.9a, the coil is subdivided into 2 or 3 or more coils lodged in adjacent slots. Okay, so there's slots cut in the stator. You lay these coils in there. All right, and the staggered coils are connected in series, and they constitute what is known as a phase group. Now, there's to get a picture of what we're talking about here, and this is, I know this is hard to visualize. He says if we look at 1320 here, this is what he's talking about. Okay, so this is a coil of wire, and if you look at this carefully, you'd see that all of these are, they're all connected together, and here's one side of the coil and here's the other. And what you do is, you lay these individual coils in the appropriate slots in the stator, and they cover a certain amount of area, like we were looking at in the earlier slides. Okay, so you have a certain number of coils per group, and if I look at this one, there's 1, 2, 3, 4, 5 coils. So there's five coils per group, and this all together is something that we call a phase group. A phase group, or simply group, and it's composed of the staggered coils that again are laid out into the slots. All this is done symmetrically so that you get this continuity across that stator. All right, so that's 13.4.